Hey guys, today we're going to start covering the most important tool, the most useful tool in all of digital circuits. And I know that last homework you did was pretty tough, right? Especially the part we had to simplify. It was really difficult to know which rule do I use, and even if we got all the way to the end, was that as simple as it could have been? Maybe there was a different path you could have taken to make it even simpler. In fact, there's one problem on the homework that was so hard, I'm pretty sure nobody's going to get to the actual simplest form. And so because of that, we developed a tool. It's called a Karnaugh map. These things are great for a bunch of reasons. The first is that using Karnaugh maps, we can design any circuit from scratch. You might be thinking after we're watching all these lectures, okay, I kind of get what's going on, but how would I ever design a circuit to do something? Like, let's say that I had this truth table. And so, for instance, let's say A is one type of sensor, B is another type of sensor, and C is another type of sensor. Well, I know if these three things happen, I need to set an alarm on. And if this happens, I need an alarm on. But I don't need an alarm for these things. Right? How do we go from something like this to the circuits we've been seeing so far? That's what Karnaugh maps do. As long as you can make a truth table, as long as you know what the inputs are and what you want the outputs to be, you can design any circuit possible using just the K-map. Second thing we can do, we can use it to simplify circuits. We don't have to worry about those rules and worrying about whether if somebody else did it some way simpler, maybe it could have been better. I don't care if you have Albert Einstein and Elon Musk working together. They could not come up with a simpler circuit than you can just by doing the K-map. And so that's what we're going to start today. It's so important. Today's lecture is going to be really short. I'm going to break it up into two parts. So I'm just going to cover the first step today, and then we'll do the full K-maps next week because I don't want to overload you. Make sure you keep up with this. Review it a couple times if you don't understand it. Honestly, it's pretty simple. At least the way I do it's pretty simple. I think you'll be all right. So what do we need to know? To simplify a circuit using a K-map, you've got to be able to come up with the truth table. And so the problem is, if I have, let's say, an equation like this, A, B naught, or C, A, C, something like this, right? I need to know where are the ones. I need to know every place that this is true so I can create a truth table like this. So that's what we're going to learn how to do today. I mean, I could think about it. I could say, well, if A is 1 and B is 0 and C is 0, I can kind of, poke around at it until we figure it out. But there's a much easier way. So that's what we're going to talk about today. How to put an equation in sum of products form. And again, really what we need to know here is how to find out where an equation is true, all of the different places. And so first thing we need to know is what is sum of products? Sum of products are essentially all the equations we've been looking at before. So let me give you an example. Let's say I have an equation AB or A naught B D or A naught C D. This is called a sum of products because if you notice, it's the sum, so the addition of a bunch of different products. Remember, product means multiplication. And so a sum of products equation is just one where you essentially have a bunch of AND gates all being connected with a single OR. Now the good thing about this is it's really easy to get there. To turn any equation into a sum of products, all you have to do is distribute everything. Basically just multiply everything out. Let me give you an example. Let's say we had an equation like this. A, B, or C, or AC. Notice this would not be a sum of products because we've got a bunch of other complicated stuff here happening. But if we just multiply it all out, so I do A times B, or A times C, or AC, now notice it's a sum of products. We have a bunch of products being summed. And so that's why this is easy. If you ever need to get there, you just multiply everything out. Distribute everything, and you'll always be left with a sum of products. We need to take it one step further, though. we need it to be a standard sum of products. And what that means, if it's the standard sum of products, is that every term, so every product, uses every letter. And so if we look at this first case, this would be sum of products, but it would not be standard sum of products, because in this one, C is missing. Notice it's just AB. In this one, B is missing, and in this one, B is missing too. So sum of products would be like this. Standard sum would be like this, where every single equation has every single letter. Notice that all three of these have all three letters. Alright, so that's what we want to figure out today. How do I get to an equation that is in sum of products where every single letter has every value? Because notice, if it has every value, I know exactly where this equation is going to be true. This equation is going to be true when A equals 1, B equals 1, and C equals 1. Because then we'll have 3 1s going to an AND gate. It's going to be true when A equals 1, B equals 1, and C equals 0. Because again, remember the C gets inverted, and so the AND gate will have all 3 1s. Or it'll be true again when they're all 3 the same. And so that's our goal. Once I have this, I can fill out the truth table. Alright, so first thing I want you to know, let's look at how the book does this. So I've been doing this for a lot of years, and I found a much quicker way to find out every place that it's true than the book. And I'm going to teach you that in just a second, but so I don't confuse everyone, I want to show you how the book does it. So let's look at this problem right here. First thing we need to ask ourselves, is it in sum of products form? It is, right? Because notice we have one OR gate connecting a bunch of products. So we have a sum of a bunch of products. So it is in sum of products form. Is it in standard form? What do you think? No, it's not, right? Notice that this equation has A, B, and C, but this equation here only has A and B. It's missing the C term. And so this would not be in standard sum of products. So what we need to do is we need to put it in standard sum of products. Okay, so here's how the book does it. The first thing we have to know is, what would this be? C or C naught? This was one of our rules, right? So what would this always be? Well, if we remember, this is always true, right? Because, think about it. If C is 1, then C naught has to be 0. But 1 ORed with 0 is always 1, because for an OR gate, only one of the inputs has to be true. If instead C were a 0, then C naught would have to be a 1, because it's the opposite of C. And so notice that it would still be true. And so remember, we said that this is one of our rules. C or C naught always has to be equal to 1. Alright, remember also, just like in multiplying, you can always multiply any equation by 1 without changing its value. So that's the way that the book does this. Let me show you here. So notice in this first equation, we're missing C in the first term. And so what the book says to do is this. A naught, B naught, and multiply it by C or C naught. And remember, that's okay because we're just multiplying by 1. Or A, B, C. Still with me? Now we just need to distribute everything. So in this case, I would have this times this. So A naught, B naught, C. Or this times this, which would be A naught, B naught, C naught. And then finally we just have the rest. Or A, B, C. So now is it in standard form? It is, right? Because notice that this one has A, B, and C, this one has A, B, and C, and this one has A, B, and C. And so now that we have it in standard form, we can really easily find where the true points would be, right? This first one is going to be true when A is 0, B is 0, and C is 1. Because the A and the B get inverted, so they get turned to 1s, and then we have 3 1s going to an AND gate. This one will be true when A is 0, B is 0, and C is 0, because they both have the inverts on top. And finally, this last one will be true when A is 1, B is 1, and C is 1. And so now when I want to fill out this truth table, all I need to do is go to those rows. So it will be true at 0, 0, 1, it will be true at 0, 0, 0, and it will be true at 1, 1, 1. Everywhere else we know has to be false. And so we've really quickly filled out that truth table without having to do any extra work. Let me do one more example, the way that the book does it, just to show you why it's not very hard, but it can take a long time. Okay, so for this example here, we need to find out everywhere this circuit would be true. So our first question, is it in sum of products rather? And the answer is yes. Notice that it's a whole bunch of products, a whole bunch of AND gates connected by an OR gate. So it is in sum of products. Is it in standard? And the answer is no. This one here is missing D. This one is missing C and D. And this one is already in standard form. So if we do this the way that the book does, I need to add D here and I need to add C and D here. So to do that, I would do A, B naught, C, and I would multiply it times D or D naught. For the second one, we would have A naught, B naught, and I'm going to do them step by step. So I'm first just going to add C, C or C naught. This one here is already in that form. Now I'm going to go through and multiply everything out. So this first one becomes A, B naught, C, and then we have multiplied by D, or A, B naught, C, D naught for this multiply. The next one, we have A, B naught, C, or A, B, C naught, A naught, B naught, C rather. See, it's really simple to make a mistake. I almost made a mistake there. For multiplying that times that, and that times that, or the last one is already done. A, B, C naught, D. Now notice, we're not done. This one is in right form, this one's in standard form, this one needs D added to it, and this one needs D added to it. This one is in correct form. So we have to go ahead and add those D's. So that would give me A, B naught, C, D, or A, B naught, C, D naught, or A naught, B naught, C, and again I'm going to multiply it now by D or D naught. Next we've got A naught, B naught, C naught, and I'm going to multiply that by D or D naught, or A, B, C naught, D. Last, we just got to multiply everything out. So we have A, B naught, C, D, or A, B naught, C, D naught, or A naught, B naught, C, D, or A naught, B naught, C, D naught. So I just multiplied this times this and this times this. I'm going to do the same thing here. This times this and this times this. Or A naught, B naught, C, D. Or A naught, B naught, C naught, D naught. Or A, B, C naught, D. And so that's it. Now notice that every single one of these AND gates has all 4 letters. And so if I need to know where it's true, remember if it doesn't have a bar, you write a 1. If it does have a bar, you write a 0. So 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0. Oh, the last D doesn't have a 1, doesn't have a bar. 1, 0, 0, 0, 0, and 1, 1, 0, 1. So these are the places that this circuit would be true. And again, we're only doing half of it. Next week, we would see exactly how to use this to use a K-map to shrink these circuits. So notice, this isn't very hard. We always do the exact same thing. It's the same pattern we follow. But it can take a long time. It's a lot of writing. You may be more likely to make simple mistakes by leaving off a dash. I want to show you guys a shortcut way to come up with these values, because that's really what we need, is to get these values where it's a 1. If the way that I do it confuses you, you can continue to do it this way. There's no reason to use my shortcut. I don't think my shortcut's in the book. It's just something I made up. Let's take this original circuit. I'm going to take it and do it my way. So A, B, what was it? A, B naught, C, or A naught, B naught, or A, B naught, A, B, C naught, D. Alright, so here's how my shortcut works. The first thing we have to notice is in our equation, we need to identify the ones that are missing. So in this one, I need to leave a space for D. In this one, I need to leave a space for C and a space for D. And this one here has all 4 combinations. So, the first question, if I'm missing only one number, one letter, how many combinations could that thing be? Well, this could only be a 0 or it could be a 1. And for both of those values, this has to be a 1, this has to be a 0, and this has to be a 1. This has to be a 1, this has to be a 0, and this has to be a 1. For this one, we're missing 2 values. And so remember our equation, 2 values means that it could be 4 possible combinations. Because the 2 that are missing could be 0, 0, they could be 0, 1, they could be 1, 0, or they could be 1, 1. I'm just counting. But no matter what they are, these 2 always have to be 0. Because they have the overbar. And so notice, the reason this works is if A naught is 0 and B naught is 0 and C is 0 and D is 0, this is going to be true because C and D don't even matter in that equation. And that's why we have to add all possible combinations. For this one, nothing's missing. A has to be 1, B has to be 1, C has to be 0, and D has to be 1. And that's it. If you notice, if I compare it to up here, so we had 1011, which we have right here, 1010, which we have right here, so those 2 are done, 0011, which is this one, 0010, which is this one, 0001, which is this one, all 4 zeros, which is this one, and 1101, which is this one. So you notice you get to the exact same answer if you do my shortcut method. So what I'm telling you is whichever you are most comfortable with, do it that way. In real life, nobody's ever going to ask you to go from these numbers back to the equation, right? These numbers are what we're trying to get. It's the whole reason we have standard form. But if for some reason, like on a homework or something, you needed to get back to the original equation from the shortcut, just write the letter when it's a 1 and write the overbar when it's not. For instance, the first one would be A, B naught, C, D naught, because it's 1, 0, 1, 0. The next one would be A, B naught, C, D, because 1, 0, 1, 1. And so like I said, in the real world, I don't think you're ever going to have to do that, but if you take somebody else's class somewhere in the future and they ask you how to do that, even if you use a shortcut, you can still get the full equation if you want it. Okay, let's try a few extra examples just to make sure there are no tricky cases. So the first question we have to ask, is this in sum of products? And the answer is no, right? Because notice that it's not just a bunch of AND gates connected by one big OR. And so remember, the first thing we always need to do is multiply everything out. And so I said, if you have like parentheses, always start at the innermost and work your way out. So this equation here would become, notice I'm not touching anything on the outside yet. So I first multiply this, we would have BC or BD. So I just multiply that and that. Next, we keep multiplying, so now I have to distribute this. So we have AB or ABC or ABD. So far so good? Alright, now let's put it in that standard form, and we'll use my shortcut way. So notice this one is missing C, and this one is missing D. This one is missing D. And this one here, notice it's missing C. Here's something really important. You have to keep them in the right order. So C is missing between B and D. Alright, we're missing two values here. And so since I'm missing two values, that means there are 2 to the n. So in this case, 2 to the 2 to the 2 values missing. So that means we have 4 combinations. Those could be 0, 0, 0, 1, 1, 0, or 1, 1. A and B, in this case, always have to be 1. And so those are the 4 values the first term will be true for. The second one is only missing D, so that could either be 0 or a 1. But for all 3 of these, it has to be 1. Finally, for the last one, we're missing one value, just C. So that could be a 0 or it could be a 1. But A, B, and D always have to be 1. See? Not too bad, right? Let's try another one. So here we have another one. Notice this one's a little bit trickier. First question, is it in sum of products? And the answer is yes. It's a whole bunch of ands. Notice that this one's by itself. That's still okay. It's still connected with a bunch of ors. So it is in sum of products. It's not standard though. Each one is missing stuff. So it's not standard. So again, we're going to use the shortcut. Notice in this case, what's missing? A and C are missing. So again, it's really important that we keep them in their right order. And so we have 2 that are missing. So that means there's 4 combinations missing. So that A could be a 0 and C could be a 0. A could be a 0 and C could be a 1. A could be a 1 and C could be a 0. Or A could be a 1 and C could be a 1. So those are the 4 that are missing. For all 4 of them, B has to be a 1 and D has to be a 1. Alright, let's try the next one. What's missing? Notice we're missing B and C in this one. And so just like before, there's 4 combinations we're missing. 0, 0, 0, 1, 1, 0. And let me write it a little bit bigger. It's all squished in there. 0, 0, 0, 1, 1, 0, and 1, 1. And for all 4 of those, A has to be 0, and D has to be 0. Finally, this last one, look how much we're missing. We're missing A, we're missing B, and we're missing D. So if we have 3 that are missing, that's 8 possible combinations that we're missing. So that would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Notice we fill this out just like a truth table or just like we're counting. 1, 0, 0, 1, 0, 1, 1, 1, 0, or 1, 1, 1. So those are the values that we're missing. For all of those values, C has to be a 1. Last but not least, I want to show you one thing that'll help you write these out. We have a shortcut way to write equations when we're talking about digital circuits. Instead of writing this, you can see how many terms this one has, right? It would take me forever to write out all the values. but we have a shortcut. What we can do is convert each of these to their binary values. So this is the number 5. This is the number 7. This is 8 plus 4, which is 12, so this is 13. This is 15. This is the number 0. This is the number 2. This is the number 4. And this here is the number 6. I'm just converting, right? This would be the 1's place, the 2's place, and the 4's place. So that would be 4 plus 2, which is 6. That's how I'm getting these. This would be 2. This would be 3. This would be 6. This would be 7. This would be 10. This would be 11. This would be 14. And this would be 15. So say the problem asked you what would be the values in standard form. We can also write it like this. I can say I have a digital circuit that's made up of A, B, C, and D, and its sum of products is true at 0. Took care of that one. It's true at 2. So took care of those. It's true at 3. It's true at 4. It's true at 5. It's true at 6. And it's okay if it happens twice. Once we get the K-mapping, we're going to be able to simplify it. That's the whole point of getting these values. It's true at 7. I had to pick one where they're almost all true. It's true at 10. It's true at 11. It's true at 13, 14, and 15. So again, I just wanted to show you this because one, it can make it easier for you to write it all out, but you might encounter that in the real world. Somebody might say, build this circuit that's true at 0, 4, and 7. That means these are the spots in the truth table that have a 1. That's true. So I know this still seems a little bit abstract to you, right? We haven't actually built circuits with it or simplified it. We're going to do that next week with K-mapping. I just didn't want to throw everything at you at once. Please practice this before next week, because next week we're going to have to do this as step 1 to complete the K-map. As always, if you have questions, you know the multiple different ways to contact me. I'm here to help you. Just let me know.